the letter F. We haven't done a case where we need to use the integral yet, so we're going to do that also. We did just the summation format. Then we got into moment of inertia. Okay, with moment of inertia, how much did we cover? Well, we used this equation to find the moment of inertia of a rod about its center. So that's 1/12 ml squared. Then we learned to shift it to any point, such as the end, or any other random point. So we used this one, and we did the parallel axis theorem. So we did this, we did this. So what's left to do? Oh, we also did spheres, the integral for the sphere, moment of inertia of a sphere around its center. That one, I showed you how to do the integral with single integrals or triple integrals. All right, and then the solid sphere comes out 2/5 mr squared. Then you can shift it also, once you get that, you can shift it to any point. Then we did the cylinder. Okay. So then we can go back to, let's say, we can go back to one of these and say, how do we find the moment of inertia of something like this, or something like 11? Okay. So then that would be a case where, like this one, we don't have to integrate, but we just need to know the moments of inertia of the individual pieces, right? So with that case, we're going to use this equation, but this one is a little bit too simplistic. It only works if the masses that you have are point objects, like they don't have much dimension, and then they're connected with a string. And then you have another object, then you have a string, another object. So if the strings didn't have any mass or weight, and you wanted to find the moment of inertia around a certain axis, the only masses would be the point objects. Then you would just straight use this equation. The mass of this times its distance squared. The mass of this times its distance squared, right? That's when you use this one. When the object doesn't have dimension. And then when the mass of this times its distance squared, and then the mass of that times its distance squared. And then that will give you the total moment of inertia of the whole shape about that axis. So that's a case where to use this one. Now, if I'm going to go to something like this, I'm going to say, what's the moment of inertia of this? Around what axis? Well, around the center, around here. I could do any axis. Then I could do the center of mass axis, wherever the center of mass is. You know. So let's go back to that one that we did. We already know its center of mass. I think it was a ball and a rod that were glued together. It's kind of similar to this. In this case, you've got two balls and a rod. So on the test, I could ask you variety. Two balls, rod, and another rod that's embedded halfway into this ball, you know. So any kind of variety of that. See? So the first thing to do would be to ask, where's the center of mass of that shape? So in the case of these two balls and the rod, center of mass happens to be here. And they nicely go around their center of mass, right? So this is illustrating the concept of center of mass and also the concept of binary stars. Because this is a heavy star and that's a light mass star. And they go around their common center of mass, you see. So binary stars are very common in the universe. Now the actual midpoint of the rod is this. You see, they don't nicely go around their midpoint because this is heavy. It causes a net torque, right? So the midpoint of the rod is not the center of mass of the system because this is much heavier. But we could do a swinging problem. We could swing it here and say, what's the velocity of the black ball when it reaches the bottom? These class of problems are very common. They're called swinging problems, right? So what was the shape that we had for that problem? We did it back in chapter 9 when we learned how to find the center of mass. What was the mass of the ball? Let's just work with that same ball. Okay, 8 kilograms. And then what was its radius?
2 meters.
Okay. And then this one was?
Oh wait, the ball was 10 kilograms.
Okay. And then what was the mass of the rod?
8.
And the length?
5 meters.
And was the rod embedded all the way to the center, or was it glued to the end?
It was glued to the end.
Okay. And where did we find out the center of mass of the system is?
Well, we put the...
Remember, we prefer to put the XY at the center of the ball, but we didn't have to. I showed you how we would do it if it's not in the center of the ball, right? But no matter where you put it, you get the same answer. I think it was still inside of the sphere, right?
No, the sphere was 2 kilograms.
Oh, 2 kilograms.
Yeah.
And the radius was what?
The radius was 2.
Both?
Wait,
You sure?
I have 2 meters and 10 kilograms.
Oh yeah?
Yeah, that's right, 2 meters for the radius.
Yeah.
But 10 kilograms though.
Mm-hmm.
Yeah. Oh,
Yeah.
So I think it was right where the sphere ended.
Oh yeah, it happened to be right at the interface.
Yeah, it
That's
was
really
4 to the
weird.
right.
It happened to be right at the interface was the center of mass. That's weird because that's kind of usually not the case. In this system, they've actually drilled a hole right there. It's a little bit outside. The center of mass of the Earth and Sun system is where? Earth, Sun. It's actually, if this is the middle of the Sun, it's like right here.
Oh.
So the Earth is going around the Sun while the Sun is also going around that. It's wobbling. You see? So the Sun is literally doing this. Once every year. Once a year. And then we're going like that once a year.
So on a bigger planet like Jupiter, it'd still be in the sun, but
Yeah, the Jupiter will be like kind of farther away. 5 times farther away than the Earth. Yeah, Jupiter's like right here. But that moves the center of mass slightly, a little bit more over. Maybe here. So now the Sun does this. Yeah. Okay, so someone in another solar system, how can they discover us? Look at the wobble of the star, right? And you can determine how many planets it's got, and their masses of the planets, and their distances to their stars. This is what the Carnegie Observatory guys do, right? They look at all this data of star motion and star spectra, because when the star is doing this, once in a while it's coming toward you, then when it's going away from you, toward you, away from you. So when it's coming toward you, spectral lines are blue shifted. When it's moving away from you, red shifted. Blue shifted, red shifted, right? The Doppler effect, right? So when the star is wobbling, we can study the Doppler effect of that star. put it through our computers, Linux system, right? Study all that data. You can determine the elemental makeup of that star, the wobbling. You can determine how many planets it's got. You could do your center of mass calculation, find out what the masses of the other planets must be.
You know, since Pluto is like really far away.
Yeah,
Is
it's
it
not going to affect the sun much.
No, but would its center of mass be outside of the sun at that point, or no?
No.
No, it can't be.
The
No,
mass
otherwise it
of the
wouldn't.
sun is more than, I believe it's more than the mass of all the planets combined, and a lot more than that even.
Right.
You know?
But that's why like Pluto had like a weird orbit, right?
No, that's not for the center of mass. It has nothing to do with that.
it,
No,
okay.
no, it's just the birth of Pluto, and it's more like it's a Kuiper belt object more rather than a planet.
Yeah.
Yeah. Okay, so now if I want to find the moment of inertia of this about any axis, I could do it again, the moment of inertia around this axis, right? I about the center of mass of the sphere. So then we would have to know if it's a solid sphere or a hollow sphere. For the center of mass, we didn't need to know whether it's a solid or hollow. But for the moment of inertia, we do need to know, because the moment of inertia of a hollow is bigger than a solid, right? So if it's a hollow sphere, so we would add the moment of inertia of a hollow sphere about its center, plus the moment of inertia of the rod about the center of the hollow sphere, right? About the center of sphere. Because what we're doing is we're finding the moment of inertia of the system about the center of the hollow sphere. You see? So then we go I center of mass of the sphere, or I could say I total center of mass of the sphere. What's the moment of inertia of a hollow sphere? 2/3, right? 2/3 mr squared. So then we're going to multiply the mass of the ball times the radius of the ball squared. Okay? So the moment of inertia of the hollow sphere about its center is 2/3 mass times radius squared. Plus, what's the moment of inertia of the rod about the center of mass of the hollow sphere? Then we use the parallel axis theorem, right? 1/12 ml squared, 1/12 ml squared plus md squared, right? Parallel axis theorem, we should write that down, very important. ICM plus md squared, right? So 1/12 ml squared plus m times what's the d? The d. The d is from here, shifted all the way to the center of the hollow sphere by that distance. So what's that distance going to be? 2.5, right? 2.5 plus 2, 4.5. So 4.5 squared. So 1.5, 2/3. This is the moment of inertia of the hollow sphere about its center. The moment of inertia of the rod about its center, plus the moment of inertia of the rod shifted to the center of the hollow sphere. Okay, so calculate that. Let's see what we get. 288.67.
288.667.
288.667 kilogram meter squared.
Or wait, hold on, but I got divided by 2 instead.
It's 205.
Yeah,
Hmm?
205.33. Yeah,
205?
yeah. 1.3 repetitive.
205.333. But I'm just keeping this here just in case, because here's how I'm going to show you how you would know if it was wrong. What you can do is, let's assume you calculate that. Let's assume you calculated this. Then the next step would be to calculate the moment of inertia of the system about its center of mass, about the center of mass of the system, not the center of the hollow sphere. So how would we do that? We would apply the parallel axis theorem to the system as a whole, not just the sphere, but the system as a whole. We would say the moment of inertia of the system about any axis is the moment of inertia of the system about center of hollow sphere. No, hold on. Moment of inertia of system about any axis is moment of inertia system about center of mass of system plus the mass of the system d squared. Okay, so now the moment of inertia system about any axis, in our case we found out the moment of inertia about the center here, right? So then that's my 288.667, let's say. Let's assume we had calculated that. Then we would say moment of inertia system about its center of mass, we don't know. I total about its center of mass, plus what's the total mass of the system? 10 plus 8, so that would be 18, plus the distance would be the distance from where you found it to where the center of mass you found from chapter 9, right? So that it happened to be right at the edge, so the shift is from here to here. So that would be a shift of 2, literally. So this is what I call shifting downwards. Why? Well, you're using the parallel axis theorem to shift down. It's like almost a shift in the car when you shift your gear from the higher gear to the lower gear, right? So you're shifting downwards to find this moment of inertia about the center of mass, which is less than that. So you're basically subtracting this. Or but you're doing 18 2 squared, the distance squared. Do you see what I mean, shifting down? You shift down from any axis down to the center of mass to find the center of mass of the system about its center of mass, right? The moment of inertia of the system about its center of mass, which is the lowest moment of inertia of the system, right? So then you go I total about its center of mass. So 288 minus 18 times 4. So what would that give you? 18 times 4 is 72. 72 subtracted this, you would get 216.667. That would give you the moment of inertia of the system about its center of mass. Then you can shift upwards to any other point that you want using the parallel axis theorem. So we can shift upwards to the middle of the rod, right? So then the moment of inertia of the system about middle of rod would be what? I total Cm plus m total d squared. So then you get 2, now you're shifting up again. Shift down, shift up. Total mass of the system, 18. Then what's the distance there? 2.5, right? 2.5 squared.
you're saying we get the center mass of two objects, we find that center, and that's the distance, and that's what we're using. Okay, okay, sorry.
Yeah, you're taking the center of mass equation that we've already done back in chapter 9.
Yeah.
We're saying,
Each
but
object
first
is-
calculate the moment of inertia about the center,
Right,
then shift down to the center of mass.
Right.
Find the
For
moment
the
of
whole
inertia
thing.
about the center of mass.
and we do the same thing with the other
Then you
object.
can shift up to the,
Oh, we shift up. Oh.
you shift up to the middle of the rod or to any other point that you want,
Oh, okay.
right? Okay. So then what would that be? Someone calculate that. I'm assuming we still got the answer 288, you know.
That's 329.
1667.
329 point.
667.
167.
Now, how am I gonna catch my error? Here's the trick. I can independently calculate the moment of inertia of the system about the center of the rod, right? Without using any parallel axis theorems stuff, without shifting down and up. So how would I do that? Well, I would do similar to what I did here. I would calculate the moment of inertia of the rod about its center. I would calculate the moment of inertia of the hollow sphere about the center of the rod, right?
This way, and that way, we're comparing.
Well, this one, yeah, this one you don't have to shift it because it's already at its center,
Oh.
right? So I total of system about the middle of rod is gonna be what? Well, for the rod, I just use 1/12 ml squared. Plus, for the sphere, I shifted, right? So 2/3 mr squared plus md squared. So 1/12 times the mass of the rod is 8, times the length is 5 squared. And then 2/3 the mass of the sphere is 10, its radius squared, plus the mass, right? The mass of the sphere, right? But then shifted. See here, we didn't shift the sphere, but we shifted the rod, right? There, we don't shift this rod, but we shift the sphere. And what's the shift amount? It should be still 4.5, right? Just like here, we had 4.5. Shifted, we shifted from here to here. Now from here to here, it's 4.5 again. But now we're shifting the sphere. So we're using the mass of the sphere, right? That's the difference. Okay, so now let's calculate that. If we did everything right, that answer should match this answer, 329. If something in our calculations is wrong, then that's when the alarm bells ring. Okay? 245 point.
833. 8 repetitive.
Now what should that equal? 329. Yeah, see? So something goes wrong. Something has happened. That's how you know you've done something wrong. So now you go back to, let's say you don't know where the error is from. You go back to here, you do recalculate it, you say, oh, okay, I'm actually 205 here. Then you put 205 here, right? And then you calculate this again, shift down, shift up. And let's say they match, then you know everything is right. Let's say they still don't match. What else could be wrong? Let's say you do that, you correct it to 205, you do shifting down, shifting up, and they still don't match with this. Well, maybe this could be wrong in your calculation,
Oh, we put the wrong
but let's say you
equation.
check it and nothing is wrong. But there's still something that could be wrong. Even if you've done all those checks.
We're using the wrong equation.
No, not the wrong equation. The one that could be wrong is the center of mass that we calculated back in chapter 9. You see?
Yeah.
That's what happens a lot of times. If you get the center of mass wrong, what's going to happen? This is going to be thrown off. This is going to be thrown off. The center of mass of the system is wrong. It throws off everything, ICM and everything, right? So let's see now. This is our chance to really check. Put 205 here. 0.333. Shift. Take 18 to square. Subtract 72. That will tell us the moment of inertia about the center of mass of the system. So 205 minus 72, that's going to give you no, 3, right? 133, is that right? So this is the moment of inertia about the center of mass of the system, the total moment of inertia about the center of mass. Then shift up. And if that gives you 245, then that's it. Drum roll.
Yeah, it's exactly.
That means the center of mass you got right also, back in chapter 9. Let me see. Because the moment of inertia, parallel axis theorem only works if your center of mass was done correct. You see, that's how you can catch any other errors that you might have made. Okay? So now we know how to do these kinds of things just by summing up, summations, using parallel axis theorem and checking to see if our answer is right. Now let's do a swinging problem with that. Suppose now that system is pivoted about its center and now allowed to fall, right? So then we could even have it go like this. Start from the top position. Imagine the ball is like this. And now the pivot point is here. The center of the rod. Now I allow it to fall, what's going to happen? It's going to start rotating. This is what's known as an unstable equilibrium, right? Remember chapter 8? Points of highest potential energy is unstable equilibrium. Because a little displacement from it will cause it to want to go towards lower potential energy. You see? So now, when it rotates, when it reaches the horizontal position, I want to calculate the velocity of the center of the sphere and the acceleration of the center. Right? And by the time it reaches all the way down to the bottom, I want you to calculate the velocity of the center and the acceleration of the center as well. So this is a swinging problem. So how do we do it? Well, to do velocity, you use potential energy, kinetic energy method. To calculate acceleration, you use torque method. You see? So for velocity, you do the initial potential energy stored in the rod converts into kinetic energy. What kind of kinetic energy do swinging objects have?
Rotation.
Remember in the lab I taught you only rotation, not translation. Wednesday we're going to start the problems on rolling motion, and rolling objects have translation and rotation. See, so this one is only rotation. Okay, so the mass is the mass of the system, which is going to be 18 kilograms. What's the height? In other words, what's the height of the center of mass of the system as compared to its final height, right? So center of mass is right here, right? At the edge of the ball. And the initial center of mass is also at the edge of the ball. So let's always make the lowest position it's 0, right? So the initial height of the center of mass is going to be 2.5, right? It's the distance from here to here. So mgh, what's h? The distance from the center of mass at the end from the initial location of the center of mass. You see? So that's going to be 2.5. Half I. What's the I? I is the moment of inertia about the axis that you're rotating it around, which is the middle of the rod. So which one is that? 245. You see? Okay? Using that, calculate the omega final. That will give you the angular velocity of the system when it reaches the horizontal position.
Can you, why is H 2.5 again?
2.5. Yeah, it's the distance from here to all the way to the edge.
Oh,
So
that's, oh, okay.
Yeah. Go ahead, ask. This is your chance. No wrong questions.
So it's 2.5.
I didn't write it, draw it, but because it should be same as this. It's symmetric. Because mgh, h is the distance from the center of mass to the reference point,
Okay.
right?
Oh, okay.
And then the moment of inertia, is not with is with respect to the pivot, you know, what axis it's pivoting around. You see?
Yeah.
So since it's the middle of the rod, you're doing
It
this.
just threw me off because it's right at the edge, like center mass is right at the edge of the sphere and the rod.
Yeah.
So it threw me off that it was also the midpoint of the rod. And my brain thought we were just finding the center mass of the rod. But now that's where it's pivoting, so my brain just,
Yeah. So you can't do swinging problems around the center of the system, because around the center of the system, it's not gonna swing. I can exert the torque and make it swing. Then that's an external force, you see. But it won't swing due to its own weight, because its weight is concentrated there, you see.
But that's kind of what we're shooting for. If we're making something, we're going to rotate a lot, like a wheel or.
Yeah, but
It has
when
to.
we're doing the swinging problem, I'm
Yeah.
defining the swinging problems as swinging due to its own weight.
Its own weight.
So then we pivot it at a point away from its center, and then we have it swing, you know, like that.
Okay. Okay, nice, yeah,
Yeah.
I see what we're doing now.
Okay, what's omega? Huh? 1.894 rads per second. Once I know omega of a rotating object, how do I find the velocity of any point of the object? What equation is there that connects the v tangential to the omega?
The tangential is r omega.
Or r omega. Remember, S is r theta, V is r omega, A is r alpha. Those are equations. Very important. S is r theta. So once you know the omega of an object, the farther away you are from the pivot point, the faster you will be traveling. Right? So if I want to know the V of the center of the sphere, V of the center of sphere, and that's going to be 5 plus 2, right, is the distance here. No, what am I saying, 5? This is 2.5 plus 2, right?
Yeah, that's where I got lost.
Yeah, it's 2.5, not 5. Because from here to here is 5. But from here to here is 2.5 plus 2, 4.5. So then it's going to be r omega, where r is going to be 4.5. So almost 9. Okay, how about the velocity of the center of mass by the time it swings all the way down to the bottom? How about the V down here? What changes? We're going to use energy method again, right? So now what's going to happen? The height is now measured from the lowest position of the center of mass. Where's the center of mass at the end? Down here. So that's your reference point now. So what's the original height of the center of mass? Instead of 2.5, it's 5. So literally this goes from 2.5 to 5, which means you double it. Well, since it's only a difference of a double, the moment of inertia doesn't change. So then the omega is going to be rad 2 times this. And that's just always going to be the case, you know? Whatever this came out, rad 2 times this, because when it goes all the way to the bottom, it goes twice the distance down. So omega final is rad 2 times 1.894, and therefore V final is going to be rad 2 times 8.523. Whatever that velocity is, this is also rad 2 times that. Okay, so that one takes care of that. Okay, how about the acceleration now? For acceleration, I need torque is equal to I alpha. The torques on the system is equal to its moment of inertia times alpha. So I need to first calculate the alpha of the system. Then from there, I can calculate the A of any point. You see? So what's the torques on the system? Well, the torque is due to its because this is a swinging problem, the only thing causing a torque is its own weight. So when it comes horizontal, the weight is mg, rmg, right? rmg, so the torque is into the board, but the into the board doesn't really matter, right? So it's an into the board torque, and the magnitude of the torque is what? rmg sine of theta, where theta is this angle. So when it's horizontal, the weight is down, and the r is like that, and the angle is 90. See? So it's gonna be, r is gonna be what? From the pivot point to where the center of mass is, it's 2.5 meters again. The total mass of the system was 18 kilograms again. G is 9.8, sine of 90. What's the moment of inertia of the system? 245 again. So the difference is that here, it's kind of looks like this, 18, 9.8 times h. This one is 18, 9.8 times h. So it's actually kind of close, right? But here, instead of half I omega squared, it's just I alpha, no half, and there's no square here. Let's see. So then this one goes down here. And then you calculate alpha. Okay, what does that come out? Okay, alpha is 1.794 rads per second squared, right? Whereas the omega is rads per second. Once you calculate the alpha, how do you get the A of any point? R alpha. You see? So that you're going to use the same R that you used here when you did the V, right? 4.5. Okay, how about when the object goes all the way down to the bottom? What's the acceleration? Now this is going to be very weird because the weight is down and the R is like that. See, when it's down on the bottom, mg is down, R is down. When you do R crossed into mg, what are you going to get? 0. So when it reaches the bottom, it's the fastest that it's moving, but it's not accelerating anymore. You see? So a swinging object is a case where,
Because it starts decelerating.
yeah, you see, the swinging object accelerates, speeds up, reaches the maximum speed. Then it continues to speed up, but at a slower and slower rate. Now it doesn't slow down, it's still speeding up,
At a slower.
but a slower rate,
acceleration.
at a slower acceleration. So it's like you getting in the car and you put your foot on the gas pedal and you increase, you put it down even more. You continue to put it down even more, Then once you reach there, you don't take your foot off the gas pedal, but you continue to press it, but now you're starting to take it out. So your foot is starting to come out. So it's still on the gas pedal, but not as hard, you see? So you're still speeding up. Right here, your foot is off the gas pedal. So that's your maximum speed, you see?
Right.
Then after that, the opposite happens, of course. Now you're braking.
Slowly break.
Yeah, you're slowly braking now.
Yeah. That makes sense.
So you're slowly braking real hard, braking the hardest, but then you still haven't stopped, right? Now you brake less and less hard. You take your foot off the brake, right? So you're kind of mapping this motion to a uniform motion of a car. See, well, of course, it doesn't go all the way up because of friction. But if there was no friction, you would go all the way back up, and then the whole thing would repeat, you know?
This is when electricity occurs, right?
Yeah,
Yeah. Like the electric.
the motor, the RPM.
Yeah. The alternating. Yeah.
Yeah.
Okay.
So that means the acceleration at the bottom is 0.
How are we gonna find out the direction of R?
It's the vector that points from the
Center.
center of the object, the pivot point,
Mm-hmm.
to
To the object.
where the center of mass is.
Correct.
Yeah. So A at the bottom is 0, and alpha at the bottom is also 0. Okay, so now we know this problem really well, a sphere and a rod. Now we can take like a letter like this. The other day on Friday, when Alan was holding his SI session, I was bored and I cut out these letters. So I made this same proportion to the one that we did. The proportions are the same, but not necessarily the lengths. So I made this guy, I think, 6 centimeters. I made that guy 30 centimeters. And I made this guy 6 centimeters. $12 centimeters. $9 centimeters. 18, 27. And 3 centimeters. When we did that problem, what did we find the X center of mass to be? Back in chapter 9. I think it ended up being in the letter itself. What was our answer? So we could just cheat and use the same answer.
X was 1.71, Y was 5.64.
1 point.
No,
5.6.
5.64.
But in that case, what was our dimensions?
We did 2 centimeters for the bottom, 10 centimeters on for the right.
So we did 2 centimeters here,
Yeah.
6 here, right?
10 over there.
Yeah, I think so. No, hold on. 2,
It was 10.
10. Yeah, okay.
6 was the
So the one I did, I made it bigger by a ratio of 3. So then I can multiply these by 3. Right? And that will tell me what my dimensions should be. So X center of mass should be 5.13 centimeters. Y center of mass should be So where is that actually? 16.92. So I'm gonna draw here, I'm gonna actually draw with my ruler 5.13, something like this. 16. Okay, so something like this. That's my theoretical center of mass, right? The bullseye. Okay, now I want to calculate the experimental center of mass. So let's do the experimental method. Yes. Yeah. Hang it from some 3 random points. I don't want to poke a hole in it to hang it because ideally, well, by poking a hole, I'm kind of changing the center of mass, you know. So if I can just freely hang it like this, I have to almost. It's hard to not poke a hole.
Yeah, maybe it's, well,
'Cause you're
not, if you're not removing mass from it, you're just pushing it.
Yeah, do you have something sharp I could use?
And like the mass is still gonna be there, you're not pulling it out, you're just compressing it around the hole.
I think
Do
you,
it with
you
the-
need to remove the lead.
Pencil.
This thing will puncture, but you just had to remove the lead from it.
Oh, there's a puncture?
There you go.
This might even count, huh? Something
Oh,
like
yeah.
that. But then I need to be able to. Okay. Well, you know what? Why don't I do this? Better. Put this here.
No.
Squeeze it till I break it. Okay. Okay, so then wait. See, it is going through that point, but it's slightly off.
I think once it settles, you just have to hold it in place. And once you see that's where the line is, you just have to grab it.
Yeah, you just have to sort of
Yeah,
grab
wait-
it.
Wait till it stabilizes. And
Yeah,
grab
grab it. Yeah,
That's good.
so it's pretty close. Then I would do another hole, and as many holes as I want, they should be crisscrossing where the center of mass is. So it's pretty close. And if I do another one, you also don't want it to be too much friction, right?
Right.
So, because then it will stay in place. You want it to be kind of loose. How did it make the lead come out? 'Cause the lead is good because it's very loose. Oh, that's pretty accurate.
Yeah.
Oh, wow. Yeah, so if we did it good and we was pretty loose, we would locate it. Yeah, it looks like we're very, very close. Nice.
Could be the cardboard slightly
Yeah, and probably when I cut it, I
Yeah,
also
it's
didn't
not.
cut it perfectly.
down to the millimeter, yeah.
Okay, so now we could go further and say, what's the moment of inertia about any axis, right? Okay. Well, that one depends on, let's say I want to know the moment of inertia about the corner axis, about the corner point, or about the center of mass, right? About any point or about the center of mass. But then the next question comes up, there's three axes that goes through every point. Every single point on the object has three axes, X, Y, Z. What axis are you going to try to rotate that around? Now, why didn't I ask that question to this? Which axis? I didn't say X, Y, Z. That one, I was pretending that the axis was this one, right? I was actually drawing them even. But there's another axis coming out of the board. Let's see, so if you take that, there's an axis, let's say a middle axis, right? There's an axis that cuts it like that, and I can rotate it like that, right? So we can call that the y-axis, for example, right? That's the one we found. And then there's a y-axis that goes through the center of mass. We can call that yy, because it's special, you know. Then there's another y-axis that goes through the center of the sphere. That's the one we found. But there's also another axis coming out toward you, that's the z-axis. Maybe like this. This one is ZZ. Z. How would we rotate it around the z-axis? If I want to rotate around y-axis, I go like this, right? If I want to rotate around Z, you see? So y-axis is this one, right? Like this. Z-axis is like this. See? The reason why I didn't distinguish them for this object is because y and z are the same. This is a symmetrical object. It's just as hard to do this as it is to do this. So I didn't have to say which one are we calculating. The only one that's different is the x-axis going through it. Then it's like this.
Yeah. Which is,
Well, the eye of the x-axis of the rod is 0 because it's dimensionless along the x-axis. It doesn't have any thickness. So the moment of inertia of this guy is 0. The moment of inertia of this guy is almost 0 because it's so small. This one is the only one that would have a moment of inertia like this. It would be 2/5 mr squared, right? But this one, okay, then I do the moment of inertia of the rod, right? This one is the same as this, so I didn't have to distinguish them. But now if I go to this, let's say the axis going like that, right? So this way. In other words, hang it from my fingers like this. You see how it's rotating? It's rotating about an axis like this. Okay, how about an axis like this? How would I rotate it?
Towards you.
Use it as a fan, right? Or hang it from those 2 points and just have it like this, like hang it from a string, or like that. Or how about an axis going x-axis? You can see, like this, or like this. This is not a very good fan. See, that's why you don't. No one says, let me take a fan out, let me do IZZ. No one does IZZ. They all know it's got to be IYY or IXX.
Wait, which one's the x-axis rotation?
Well, I'm doing it so that it's common to our, usually we call this X, right? And we call that Y, and then we call this Z. So that's why I'm keeping it that way. But it really doesn't matter what you call what.
If you rotate it about the x-axis?
X-axis would be this one.
Oh, okay.
yeah.
Now you see, it doesn't matter if you go like this, or you tilt it and you go like this. That's just, you're just rotating the basis as in linear algebra, but you're not doing anything. You can see, it's still the same moment of inertia, right? Now, how about the center of mass? The center of mass was here, okay? Which one am I doing? It's the one coming this way, right? Like this. How about if it's center of mass and going this way? So we can call this one,
On the board.
we can call this one X, Y, and then Z. IY, IX, IZ. Then the one going through the center of mass, we can call XX because it's special, right? YY, ZZ. Okay, which one is easier to find? Are these easier to find or these? In other words, if these are easier to find, if these three are easier, I'll do that first, and then I'll use the parallel axis theorems to shift up, and I can find these. But if these are easier to do, I can do those ones first and shift down to get these. So remember, shift down and shift up? So which ones are easier to do? I think these three are easier because it's an edge. It's the edge of the object. You don't have to worry about this random point. These are easier. Okay, let's see how to do them. How would you do the how would you do the IX, X? Oh, okay, good. Okay, remember how we did the center of mass? We broke it up into three triangles. Three rectangles, right? So this is the first rectangle, this is the second rectangle, this is the third. Right? That's how you would do it. Break it up into three triangles, find the moment of inertia of each triangle separately. You see? So what's the moment of inertia of this first triangle around the x-axis? So then you would ask, what did we learn about rods the other day? A rod moment of inertia around this axis is 1/12 ml squared.
At any age.
Rod moment of inertia around this axis is 1/3 ml squared.
ml squared.
Does this rotated around the x look like this rotated about the end? Huh? Exactly.
So 1/3 ml squared.
1/3 the mass of this guy times its length squared around the x-axis, right? So Ix of number 1 is going to be 1/3. What is its mass? Well, we didn't have a mass. We just knew its area, right? So what I'm going to say is the surface mass density of the F letter times the area of that. That's the mass of that. Times the length squared. Sigma over 3. What's the area? Well, I'm just gonna work with these numbers now. 30 times 60 centimeters. 30 times 6 centimeters. So that's centimeters squared, right? And then what's the length? 30, right? Times 900 over 3. 180 times 900 over 3, that's centimeters cubed, times the surface mass density. Right? But then how do I calculate the surface mass density of the object?
Total mass over.
Yeah, someone would have to tell me what the mass of the F letter is and what its total area is, right? So surface mass density, mass over area. So let's say it weighs 50 grams. And what is its total area? Well, total area is 30 times 6 plus, what was this length? Twelve.
4.
This is 12 centimeters by 3. And this is 6 by 6. So the total area is going to be 30 times 6 plus 12 times 3 plus 6 by 6. Six, 50 grams, change it to kilograms, divided by 180 plus 36 plus 36 centimeters squared. $252 centimeters squared. So So then I multiply that by the sigma by that. So this is, remember, centimeter cubed, because it's got centimeter squared centimeter cubed. Then this centimeter cancels this centimeter, right? Then I can change this centimeter. 100 centimeter is 1 meter. Then it'll be meter squared. Hold on, it should be kilogram meter squared. That's the moment of inertia should be kilogram meter squared. Do I have 1/3
Yeah, because then it cancels 1 centimeter.
centimeter? This is area 30 times 60 centimeter squared, centimeter cubed. This is surface area, right?
Yeah, you have to convert it to meter squared.
I'm missing a meter, I'm missing another meter. Centimeter cubed. Actually, this is centimeter to the 4th. Yeah, centimeter to the 4th. You know what? I'm just gonna keep it in centimeters because the numbers are gonna be too small then. It's actually centimeter to the 4th. So centimeter squared cancels centimeter to the 4th becomes centimeter squared. So I'm just gonna keep it as kilogram centimeter squared. So that way the numbers are not too small, okay? So 180. Times 900 times 50 times 10 to the power -3 divided by 3. Right, because this was centimeter squared, and this was also centimeter squared, so it was centimeter to the 4th. So all that, and we only calculated the moment of inertia of this rectangle around that axis. Okay, how about that rectangle? The I2, what is its moment of inertia? So imagine now you have this rectangle being rotated about this axis. How do we do that one? That one I can't use this guy, the 1/3, right? But can I say, oh, the moment of inertia is the axis going through the center and then shift it downwards? Parallel Axis Theorem. What would be the moment of inertia of that rectangle and an axis going through its center? Right? So what would that moment of inertia be? I, center of mass. Well, what matters is when the axis goes through its, when the axis goes this way, the dimension along the axis doesn't matter. Dimension along the axis. Only the dimension perpendicular to the axis matters. You see? So when, for example, when you have a rod, the axis that's going through the center, if I were spinning it this way, what would the moment of inertia of that rod be? Right? To this one here. Right, if I was spinning it like this, what would the moment of inertia of the rod be? Well, the axis is going through it. So this dimension, the length wouldn't matter. Only this thickness would matter. But because this is so thin, the moment of inertia would be 0 if I was doing this, right? So in this case, this dimension doesn't matter. What dimension matters? This, and if it has a dimension coming out of the board. When it doesn't have a dimension out of the board, so only this dimension matters. So the moment of inertia is 1/12 mass times this dimension squared, width squared. Okay? That would be the moment of inertia of that rectangle about that axis. This width squared. Not the length, because that's along the axis. You see?
Would
So
it
then
be
what?
width over 2, or
Huh?
would it be width over 2 because it's in the half, or it has to be width?
Well, this equation already has the fact that it's the total width. It's the total width squared, just like this equation, 1/12 ml squared, is the total length. Yeah, it already has that
But in
built in.
that case, do we still consider that's a rod?
It's like a rod,
It's like a
but the
rod.
axis, it's like almost a thick rod. It's like a thick rod. And imagine I'm twisting it around this axis. What would its moment of inertia be?
That's
1/12 m, not the L
we-
squared,
we-
but the W squared.
Oh, that still makes sense. Ooh.
Yeah, but if the rod is very thin, where the W is almost 0, then the moment of inertia is 0.
Hmm.
You see?
It's just like a pretty thick rod.
Yeah. So this rectangle is like a rod, but this dimension is not negligible. It still has a considerable dimension, 6 centimeter. It's more like a square, basically. You know. So then I'm gonna do. So let's calculate that. 1/12. The mass is gonna be the surface mass density times the area times the width squared. You know what? I'm just gonna write it like that now. Surface mass density of that. Surface mass density times area 2 times the width squared over 12. This is the surface mass density of the whole thing times the area 2 times the width 2. But then, since this is not being rotated around there, it's being rotated around here. Well, then I do the parallel axis theorem. You see? So I shift it. I about the x-axis is going to be what? Shifted plus md squared. Where the mass is the mass of that 2. Alright? So then you're going to have sigma a2 w2 squared over 12 plus m2 is sigma a2 again. The surface mass density times the area. Times the distance squared is going to be from the center of this to all the way to the bottom. So how much is that? From the center. So 12 plus 3. Right? So from the center of this guy to this guy is 3, and plus a 12, that's 15. So this is going to be 15 squared. Then I can factor out sigma a2. And this is going to tell me what the moment of inertia about the x-axis of the rectangle 2. So what's the width? The width is 6 centimeters, right? So 6 squared. So what's sigma? Well, we already know the sigma of the whole shape, and it always stays the same, uniform, right? Okay. What's the A of that? 6 by 6. 36 centimeters squared. 36 over 12, that's going to be 3 plus 225. Ix2 is going to be 1.628 kilogram centimeter squared. So I'm changing it to kilogram, but I'm keeping it as centimeter squared. The moment of inertia of the other shape was 10, so it was larger. In other words, it's larger, it's harder to rotate this around the x-axis than this. Well, it's a small shape, you know. How about the third one? Can you now figure that out by extension, right? So the third one, imagine an axis going through it. What is its moment of inertia? 1/12 times its mass times its width squared plus what? Its mass times the distance squared. Its mass is equal to what? Sigma A3 sigma A3. Sigma A3 comes out. What's A3? A3 is it's a 12 by 3, right? Right, so it's, the A3 is going to be 12 times 3, 36 centimeters squared is the A3. Then that comes out. Then you got width squared, which is 3 squared over what? 12 plus the shift amount squared. Well, the farther the object is from the x-axis, the more the shift amount is starting to dominate, you see? Because it's so far from the x-axis. So then this mass is going to be what? It's going to be, the distance is going to be, let's see, 12 plus 6, 18, plus 9, 25, plus 1.5, 27.5. No, hold on. 30, 28.5. Because it's, the halfway point is 1.5, right? Subtract 1.5 from 30, 28.5 is the shift amount. 28.5 squared. Okay, that's I x of the third. Pretty easy stuff. Yeah? Better than vectors? No, it's not easy, but it's more geometry, this section. And then really analyzing what's happening. Okay, it's almost as big as the IX1. Now we combine all the shapes. We combine this moment of inertia on the x-axis. Then we would get the I total x is going to be what? Just add them up. This plus this plus this. It's scalar. So they add up like regular numbers, not vectors. Okay? So you just add them up, you get that. Now if I want to find the moment of inertia of an axis going through the center of mass, right? Like this, going through the center of mass. See, the one I found is this one. So how about center of mass going this way? Through the x-axis like that, shift and doing this. So what would I do? Well, if I found Ix, right, then I would shift it down. By what distance? Shift it downward by the distance from the x-axis to the center of mass. which is what? My y center of mass. Shifted down by m y center of mass squared. You see? So from here, you're going all the way to here. And you go like that. You see? So when a swimmer is diving from a diving board, he's tucking his, or like this, then he's tumbling around the diver, right? He's tumbling around his center of mass. So to find the moment of inertia, treat the diver as a cylinder, find the moment of inertia around the feet, shift it down to their belly button.
The Y center.
Yeah, this axis, whatever you call it. Then you go like this, and then you're tumbling. But then as you're tumbling, you're changing the axis of rotation, because depending on the difficulty of the dive, you have to go like this, then you have to change the axis of rotation, do your little flips and stuff. So sometimes they will flip this way, sometimes this way, sometimes this way, until at the end you want to always be straight. You see. Okay, so then if I want to do IXX, what do I do? 18.145 minus m y center of mass squared. Shifting down by a distance from here to here. So what's the mass of the whole thing? Well, that one was already given, 50 grams. So I don't need the surface mass density or whatever, right? So then 50 times 10 to the minus 3, YCM, what was YCM? 16.92 squared.
Wait, why is it negative? Not positive?
I'm shifting down, because I know that this axis, I'm trying to find the center of mass. Then if I want to find the moment of inertia around another axis, then I shift up. Now if I want to find the moment of inertia around this axis, what do I do? The axis going through the top.
Shift up.
Now I go like this instead of like this, right? So what's the moment of inertia there? I don't have to start all over again to do all the pieces. God, that would be a lot of work again. I already know the I center of mass. I just shifted up to that point. Right? So I can call it y equals 30 axis. Y equals 30, the center of mass. Right? It's that horizontal, yeah.
When you say shift up, you mean with respect to the center of
It's
mass?
always from center of mass. Parallel Axis Theorem only works from the center of mass and to the center of mass.
Okay.
Yep. So then you take the center of mass plus 50 times 10 to the minus 3. And what's the shift amount? 30 minus 16.92, right? So 30 minus 16.92. So that'd be 13.08.
So you're saying with it's always to the center of mass when you go. So we can get to any point, we just have to get to the center of mass first.
Yeah, once we get to the center of mass, we can get to any point.
Okay.
That's parallel to that.
Okay,
Yeah. We can do anything.
all right. We gotta get there first.
Yeah.
Okay.
Okay. I'm not going to cover, in this course, I'm not going to cover the center of mass along the diagonal axis, keeping this, then going like that. It's too hard. It's way too hard. You can hold any axis and then have it spin around the diagonal axis. But once you know how to do the primary ones, x, y, and then shifting them, then you got the idea, you can do anything. You're gonna put all that stuff into the computer, and the computer can map it all out. Once you know, you're smarter than the computer. You gotta be able to put it into the computer, and the computer can do the calculations, right? Okay, how about if I was doing the IY axis? Piece by piece, I would have to redo them all, right? Then I would have to shift it down to the center of mass. Could we do it pretty quickly? And maybe next time, today's Monday, right? Wednesday we can do the z-axis. So IY axis would be this one. So what would be the IY of the first object? Right? Remember, the dimension along the length doesn't matter, only this thickness matters, right? And it's like taking the center of mass and then shifting it. But I'm gonna cheat. I already know that the moment of inertia of a rod about its end is 1/3. I'm not gonna use the parallel axis theorem. So I'm just gonna do 1/3 mass of the first object times its width squared. This length doesn't matter. You see? Sigma is, this is, M1 is sigma, right, times the area, which is what? So I'm doing sigma times area to get the n, right? And then the width, 6 squared. That's it, that's I1. That's really small. 0.42. Oh, you know why? Because it's like attached to it. It's very easy to rotate it. Yeah. Only 0.429 kilograms centimeters squared. Now, how about IY2? The second one. See if you can start it. I want to see if you can figure it out. Which dimension doesn't matter, determine that, and then determine how much to shift. We're doing this one now. Wednesday we might have time, we'll go over the letter P. calculate the center of mass of the letter P somewhere, well, somewhere here probably, huh?
I'm assuming that the P would form a perfect circle.
Yeah, I did a perfect circle.
Oh, okay.
I cut it as a perfect semicircle.
Yeah. 'Cause if it
So I'll
did-
give you guys the dimensions, we can work it out,
Oh, okay. Then we have to cut out the little center.
huh?
That's missing the hemicenter in the middle too. Oh.
This one probably you're gonna cut it into two pieces. One, and then this is your second one.
Right. We still have to calculate the center. has to
Then find the moment of
minus the
inertia, the moment of inertia, the center of mass.
be- oh, I had a question about, so if I pass this class, what happens? Yeah.
Hold on, let's hold that up. Let's answer this and then we'll cut the
Oh,
video
you-
and then we'll
oh,
do
you
that.
saw the
We're
video.
not done.
So I didn't know.
That was a good one.
Well, I thought we were at like at 3:30. I thought.
You know what? The lecture never ends till that thing shuts down.
Okay.
We're going.
We're almost at 100 minutes.
Oh yeah. Oh yeah. We just keep going here. We don't look at that. Okay. So what is IY2? Around. So then we're gonna do this axis shifted, right? Which dimension doesn't matter? This guy, right? So then it's gonna be 1, 12, M2. Only this dimension matters. W2 squared plus M2 times the shift amount squared. 112. M2 is gonna be sigma A2 sigma is A2 is 6 by 6, right? So 36. The width is 2. In this case, it didn't matter, right? Oh, actually, it was 6 centimeters by 6. So,
That's a 6.
so basically, it's just 6 squared. 6 squared over 12 plus the shift amount is what? 3 plus this, right? From the center. So 3 plus 6 is 9. Okay. Calculate that. .6, they're all small this time. How about IY3? Similar thing, right? Sigma. I'm gonna go kind of fast. What's the area of that? 3 by 1236 again. Okay, what's the moment of inertia? Because this part is similar, area times the sigma, and this part is gonna be this dimension. Which dimension matters here? It's this dimension that matters, right? So 6 squared, no, hold on. 12 squared, right? Because it's this, it's like halfway. 12 squared over 12 plus the shift amount is what? 6 plus another 6. Right, from here, 6, 6. So 12 is the shift amount. .114. Then add them all. Boom, boom. Plus what? This. There's one last step remaining. Shift down to the center of mass, then you can do anything you want, right? Total center of mass, 2.14 minus the mass times what? What was the shift amount? 5.13 squared. Okay. This better not be negative because then we did something wrong. Because this is such a small number, I was afraid it might come out negative. No, it's not negative. Perfect. There you go. Then we can shift it anywhere and along this axis. See, now we did this and we did this. And then Wednesday I'll do this axis coming out. Okay? We'll do that one. Okay, good, good.